I put the basic absolute value function back on the board. Y equals absolute value of x. And forgot to put my scale numbers in there. Don't forget to put a couple of those on all your graphs, because your reader needs to know what scale you're using. All right. This time I'm going to multiply the function by which I regard absolute value of x by 2. All right, so I'll squeeze it in there. And when we do that, we're multiplying the outputs by 2. So now the 0 stays the same, but this becomes 2, 4, 6, 2, 4, and 6. So it multiplying that absolute value of x by 2 doubled all the y values. So what would you expect happens when you double y values? Well, you end up stretching it vertically. And so we'll see that if you plot these points out, it's going to come out to be a narrower graph. So it looks something like this, approximately. So here is y equals 2 parentheses absolute value of x. There we go. All right. So now the vertical stretches are, I think, pretty intuitive. And I would describe this as a vertical stretch, and I do some abbreviation when I do these. A vertical stretch by a factor of 2. All right. So if I multiply by 3 instead, it would be stretched by a factor of 3. What if I multiply by 1/2? Well, it's going to be stretched by a factor of 1/2. But now here's where the language gets kind of awkward. And so let me draw that up here. Here is the y equals 1/2 absolute value of x. All right, if I did that, it's going to shrink the y values by a factor of 1/2. In other words, create a flatter graph. So here is y equals to 1/2 absolute value of x. I should draw. I'm mixing my colors here, unfortunately. That was a vertical stretch by a factor of 2. But what am I going to call this guy? I'm going to call this a vertical stretch by a factor of 1/2. Now, I kind of stew with the language on this because I think I'm being consistent with the language, but it's awkward. Because we didn't really stretch it. You know, when I think of stretch, vertical stretch, I think about pulling it this way. And actually, we compressed it. It was a compression. But I think if you use the term compression by a factor of 1/2, it's almost like a double negative. And so to me, it would be accurate to say this is a compression by a factor of 2. Unfortunately, this reads 1/2, and so I interpret it as stretched by a factor of 1/2. So when you're wrestling with the language, you can either abuse the language, and which probably sounds better, makes more sense to abuse the language, but I don't like to abuse the language because in math, language is very important. So I tend to be accurate with the language in my perception, and I would describe this flattening or compression as a stretch by a factor of, in this case, 1/2. All right, so that's the convention I'm going to adopt, and did adopt in my book as well. All right, so anyway, multiplying by 1/2 is going to flatten it out because it shrinks or compresses the y values. Now, one thing interesting is that anything on the axis never gets stretched or compressed with this kind of transformation. I mean, 0 in the y direction, it doesn't have to be at the origin necessarily. 0 in the y direction can't be stretched. You can't stretch 0. So you can only shift it. That's going to prove important a little bit later on as we apply these transformations. So for right now, we're just introducing them. Now I want to talk about the horizontal stretch, and that one, yeah, I want you to hear me out on this, but you won't need to learn it for this course from me if you're my student. Now, if you take trigonometry, the horizontal stretch is actually very, very important. If we use a wave pattern, a sine wave, for example, to describe an oscillation or a frequency or a vibration, then the rate of the vibration depends upon a horizontal stretch or compression. And so in that course, that becomes important. And actually, in trigonometry, the vertical stretch is important too, because that's related to energy levels, for example. All right. Well, in college algebra, though, the horizontal stretch for algebraic functions, very often it can be described as a vertical stretch. In fact, these can. If I were to replace in my original function x with 2x inside the absolute value, y equals absolute value 2 times x, the 2 could factor out. And what does the 2 do? When you double the x values, then when you double the x values, then you compress it this way. You compress the x's. But compressing the x's by a factor of 1/2, which is what this would do, is equivalent in this case to stretching by a factor of 2. So it's a little funny there. By compressing the x's, or stretching by a factor of 1/2, you vertically stretch by a factor of 2. Likewise, if I put a 1/2 inside the absolute value and that half would factor out, you would think of this more likely as a horizontal stretch by a factor of 2. So in other words, if you take the x values here and you stretch them out by a factor of 2, what happens when you stretch the x's? You end up with this flatter function. And so this horizontal stretch by a factor of 2 is equivalent to a vertical stretch by a factor of 1/2. In other words, a compression. So horizontal stretches and compressions work oppositely, in a sense, from their vertical counterparts. And but the kind of the good news is that the functions that we encounter for the most part when you're studying this subject, you can always, not always, but you can almost usually look at a horizontal stretch or compression as a vertical stretch or compression. There are exceptions to this rule, but so for that reason, since most of those horizontal stretches can be thought of as vertical stretches, and vertical stretches are easier than horizontal to look at, I don't worry about horizontal stretches in this course. So that's kind of my bottom line here. I want you to be sort of familiar with them, that they're out there, but I'm not going to require, if you're my student, that you know the vertical stretches, or the horizontal stretches. All right, so bottom line, learn the vertical stretches. Okay, now let's look at the idea of reflection.